The next talk is on adhesion testing plasma treated inhaler canisters, and that's by Ahmed and Mr. Bach.
Hi. Thank you. Hello, everyone. So my name is Mahmoud. I'm doing my PhD at the University of Bath with environmentally friendly plasma treated canisters. My supervisors are Dr. Matthew Jones and Andrew Johnson. So first, I thought we'd talk about what is a pressure meter dust inhaler. So they are medical devices used to treat various different lung conditions. So fundamentally, it is essentially a pharmaceutical formulation contained in a canister that, once actuated, due to the presence of a propellant on the inside of with the formulation, it causes rapid evaporation and an aerosol plume is generated. These are used for various conditions such as asthma, COPD, and not just for humans. You can see use it for an asthmatic cat as well. So pressurized dust inhalers, the majority of them are made of aluminium, or the canisters themselves are made from aluminium because it's cheap, it's light, it's very easy to manipulate. However, aluminium is a very good catalyst, and so drug formulations interact with this aluminium, and if they're in a solution, they are susceptible to degradation, and if they are in a suspension, then they are likely to adhere to the surface itself. So both of these conditions result in reduced and variable drug availability for a patient when they come and use their inhaler. However, a way to improve that is by applying a surface treatment to the internal surface of our aluminium canisters, and that will improve stability and performance. So there's several different ways you can do this. Some of the ways are anodization, acrylic polymers, fluorocarbon polymers, epoxy glass film. I'm mainly focusing on fluorocarbon polymers, which can be applied in various different ways. So you can spray dry them onto a surface, and you can also use a newer technique called plasma treatment, which is a technique which Prescott utilizes. So Prescott utilizes a technique called plasma enhanced chemical vapor deposition. So it's a combination between physical vapor deposition and chemical vapor deposition. And it results in a nano layer of FCP, or fluorocarbon polymer, covalently bonded to the internal surfaces of our canister. On the left here, you can see the actual plasma treatment taking place. So the inhaler canisters are inserted down this way, and then below is the actual plasma itself being applied to the surface. So the advantages of this type of treatment is that it uses readily available high purity industrial gases. In contrast to spray drying and other techniques which can use some very harmful solvents that are released into the atmosphere and can result in a large environmental impact. And a lot of them also use high temperatures. This technique uses room temperatures, and no waste products are produced. Anything that's not used in the process is recycled in and used again for the next batch. So on the left here, we have what previous plasma processes produced. So you can see there are issues with uniformity of the treatment around the canister. This type of plasma treatment, in theory, produces a perfectly uniform, very thin layer of FCP onto the surface. So my research is looking at seeing, does this actually happen on the inside of our canister? And some of the techniques we're using for that involve analysis of the surface properties themselves. So we're looking at surface energy. So this will involve an experiment called optical contact angle measurement. We're also going to be assessing our surface roughness. That will be with AFM. And also atomic force microscopy. And treatment uniformity, this can be done through AFM, XPS, and also scanning electron microscopy. And then we're also going to be analysing how specific drugs interact with our surface, because we are using an inhaler canister and several different drug candidates are used in this. So to do that, we're going to be doing adhesion testing. So we're going to be attaching a drug particle to the edge of the probe, bringing it to the surface and measuring the amount of energy required to pull that drug particle on. We're going to be testing it with different drugs that have different chemical properties, so we can get a little bit more of an idea of how different drugs interact. At the very end, we're going to be experimenting and testing the performance of our plasma-treated canisters compared to our untreated ones. This is to validate to see the results that we achieved up here can actually translate to real-life performance at the very end. So our test samples are three types of surfaces. We have plasma 1, plasma 2, and an untreated surface. So we use 4 canisters for each treatment. And then we split each one into several different locations on the left here. So plasma 1 and plasma 2 are the same plasma recipe, however, they are from different batches. The reason why we're testing these two ones is because visually there is a slight difference based on the color hue that comes off the surface. And we want to see if we can visually see a difference. Can we measure a difference experimentally? So the first experiment was called optical contact angle measurement. So this technique is used to measure the surface energy of our surface. Surface energy is essentially how, if a surface has high energy, it means things would like to stick to it a lot more. So we want a low surface energy surface. To measure the surface energy, we essentially place a droplet of a known liquid with known chemical properties onto a surface. We increase the volume of that droplet, and then we measure the angle that it formed before the droplet expands. That's called the advancing angle. We then do the reverse. As the droplet starts to regress, we measure the angle just before it starts to shrink, and that is the receding angle. And then once we've had that data, we can then try and get the actual surface energy from that. So from our contact angle, we need to use two different types of equations to translate that into an actual surface energy. So first equation is called the Young equation. So this just describes the balance of forces at the contact line between a liquid droplet, a solid surface, and a gas. We combine that with our Vanos-Chowdhury-Good equation, which is a very important equation because it actually breaks down our surface energy components into three different components. We have our dispersive property. So if something is interacting with our surface in a dispersive manner, it will mainly be through van der Waals forces. And then we have our acidic and our basic property. And this equation is very useful for that. There are several other equations you can use. However, they don't break down the polar component of our surface energy into our acidic and basic. Hence, this equation is selected. So once you combine these two equations, you get this lovely equation here. However, because we still have too many unknowns, we need to be able to solve for our surface energy, we need a minimum of 3 simultaneous equations. And to do that, we need 3 distinct liquids, test liquids. The selected liquids are diodomethane, which is a completely dispersive liquid, so it'll interact primarily through van der Waals forces. We also have water, which is highly polar, so it's acidic and basic. And then we have formaldehyde, which interacts primarily through basic properties. The reason why these 3 liquids in particular were selected because they have a low condition number. The lower the condition number, the better, the more accurate our results are at the very end to a true surface energy. So what we did is collected over 2,000 angles measured using our 3 different liquids at 3 different locations on 4 canisters within the same type of treatment. We then, to solve our 3 simultaneous equations, we use singular value decomposition, and then we perform Monte Carlo simulation to reveal any patterns within that data itself. And then we performed a 95% credible interval statistic to analyze if there is any statistical differences between our surface energies and our different locations, different canisters, etc. So the good bit is the data. So on this, we're showing the measured dispersive surface energy across canisters. So on the left here, we have our untreated canisters 1, 2, 3, and 4, and we can see that they are all the same. So this error bar here is our 95% credible interval. Because these bars all overlap, it means statistically, these are all the same. And the same can be seen over here with our plasma treaters. So this is plasma 1, this is plasma 2. So with our dispersive property, there is no variation between cans of the same surface treatment. This one shows our acidic surface energy. So this, on the left here, we have our untreated cans, again, showing the same thing, that there is no statistical difference between cans themselves. The reason why this is split into 2 different graphs because of the scale here is quite significant. So on our untreated cans, our acidic surface energy is all in the 23 millijoules per meter squared range, whereas for our plasma treated surfaces, we brought that surface energy all the way down to around 0.5, 0.4. So with our basic, this one's an interesting one because with our basic properties, we can see that all our error bars overlap, which means there is no statistical difference between our basic properties. So even before treatment and after treatment, the surface energy for the basic property has not changed. And it's again, similarly as before, it's showing that it's consistent between cans. So there is no variation between cans and 6 seconds. Apologies for the color on this one, but it's the same as the previous ones. We have our untreated here, plasma 1 and plasma 2, but in this graph we've selected different locations on the base of our canisters. So on the very left here, we can see that our untreated has, well, these two don't overlap, so statistically our untreated location 1, which is right in the center of our can, is statistically different to our other two zones here. However, once we've applied our plasma treatment, that difference completely wiped out. So statistically, between our zones for our dispersive surface energy property, any variation that did exist based on location has been eradicated. With our acidic, it shows the same thing. There's a difference between zone 1 and our untreated. However, once we've done our treatment, again, we're showing the exact same thing. But we can see that with our dispersive and our acidic property, the surface energy has been drastically reduced. However, with our basic property, there has been very little difference, apart from, again, zone 1. So the reason potentially why zone 1 could have a different surface energy compared to zone 2 and zone 3, due to the way that the canisters were actually produced. So they initially start off as a flat disc, then they are deep drawn into the shape of an inhaler canister. So the very base of the canister potentially could be less stretched. But once we've applied our surface treatment, again, all our bars overlap, so it gets rid of any physical or surface energy differences that occur on our canister surface. The other experiment we've been doing is atomic force microscopy. So this is an imaging technique. So the idea with this one is we're trying to identify if we can actually see a difference between our treated and untreated, or two treated and our untreated surfaces based on imaging. Because our treatment is extremely thin, we cannot tell the difference based on the AFM imaging. However, in the future, we're going to be extracting rugosity data to see if there is any measured roughness difference. And then the same thing with our electron microscopy. We've not been able to see any difference with that, which further confirms that our surface treatment is extremely thin and follows the surface topography of our surface. And in summary, so we have no can-to-can variation, and there is no statistical difference between plasma 1 and plasma 2. There is a large change in dispersive and acidic energies when the surfaces are treated, and there is little change in our basic properties, apart from in zone 1 for our untreated. So applying that surface treatment gets rid of any variation between the center, or physical differences between the center of the can and the rest of it. And also our electron microscopy and our atomic force microscopy cannot identify the treatment itself. So in the future, we're looking at extracting rugosity data from our AFM to see any difference. So that's what this will potentially look like here. And then we're also going to be performing force mapping, which is our adhesion testing, by attaching a drug particle to the edge of the probe, bringing it to the surface, and measuring the force required to pull those drug particles off. The 3 drugs that we're potentially going to be using have been selected similarly to why we've selected the 3 different liquids for our contact angle. They're trying to replicate the 3 different surface energy parameters, so we can measure and potentially predict how different drugs with different chemical properties are interacting with our surface. We're then also going to be analysing our surface composition and thickness with X-ray photoelectron spectroscopy, and also potentially doing some conductivity testing to see if there's any differences between, or any gaps in our surface treatments. So we'll measure the resistance, see if there's any gaps at all. And at the very end, we're also going to just try and see how that translates to real-life drug delivery. So I'll be using equipment just like the next generation impactor here, which simulates the different stages of deposition in the lungs. And that's all for me. Thank you very much.
Question?
Thanks, Mahmoud. That was really cool. I've got a question about the contact angles with the seasonal droplets. And this relates as well to the bouncing droplets we had before. In my experience, when you clean the substrate with different methods and different things, you get the buildup of charge, and the dispenser actually puts charge on the droplet as well. The interaction of the charge on the droplet contact angle, in my experience, was enormous. I just wanted to know if you considered charging it or trying to discharge it in some way.
That's a really interesting question. I did come across that, but I didn't measure any because we're using different liquids, obviously these different liquids will carry different amounts of charge as well. But based on the what we've seen, I haven't been able to measure or consider really applying a set charge to that. But a way of offsetting that is by just taking a load of different readings. So taking over 2,000 different measurements for advancing and receding different liquids at locations. And hopefully that will help balance out any impact that charge could have on that.
Other questions? So a very basic one, because I'm not in this area. When you think about dispensing, so a canister that has a certain volume, how does the surface property of the canister itself affect it? Because it's surface to volume ratio.
So it reduces, do you mean the, like, not talking about the contact angle, you mean the actual canister?
Yeah, it has a surface and so on, and that does something, but I'm not sure.
So even if the volume doesn't change, well, from the very start of an inhaler use, you apply, once you actuate it and measure the performance of how much drug is being administered at the very end, compared to all the way at the very last dose, there is a large variation. So that by applying the surface treatment, we're ensuring that less drug is adhering to the surfaces of the inside, and so it's more available for it to actually be actuated out. So potentially the consistency also is maintained throughout. So potentially based on volume, it shouldn't really impact it. It's just, yeah, the surface area, by reducing that surface area significantly, then we can maintain that sort of.
You should do that with the catch bottles.
Yeah.
Thank you.